Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be walking you through the chemistry class. Let's quickly consider the atomic structure. In this lesson, we'll look at the Dalton's atomic theory. We'll consider the atomic structure. We'll talk about the atomic number and mass number. Then we'll look at isotopy and then the periodic table. We'll discuss chemical combination and modification of Dalton's atomic theory. All right, let's go. When it comes to the structure of atoms, there's always been the desire to know what do atoms actually look like. Well, Mr. John Dalton came up with a theory in 1808, and in his theory he had 5 points stated. He said all matter is made up of tiny indivisible particles which are known as atoms. He was the one that came up with the concept of the atom. He said the atoms are tiny and they are indivisible. Well, later in this lesson, we'll find out how true this statement is. He also said that matter, all the particles, that is, in each element, the atoms of each element are identical to each other and they are different from those of other elements. He said when chemical reactions occur, they occur between atoms and it involves small it involves small quantities, small numbers. That is, he said when chemical reactions occur, they occur between atoms of different elements with small ratios. That is, we can have ratios like 2 to 3, 1 to 2, 1 to 3, and like that. Well, we'll see more about the Dalton's atomic theory, how true or how false it is. On your screen about now, the full atomic theory by Dalton will be displayed to show each of the points. As part of scientific quests to know more about atoms proceeded, different scientists began to observe different things, and this was one of the things that led to Rutherford's experiments. So as the quest for the knowledge about matter continued, Rutherford in 1911, that is 1911, he went ahead and conducted an experiment. That was when he discovered that the structure of the atom. In his discovery, he made an observation that the atom contained the outer shells and the nucleus. In the nucleus, which he described something as a core and orbits about which electrons did flow, and that was how we made the discovery that the atom is not indivisible. The atom can be subdivided into 3 components. These components are the negative part, which are the electrons. The negative components, which are the electrons. We have the positive components, which are the protons. And we also have the neutral charged components, which are the neutrons. Protons and neutrons. Let me correct this. The electrons, the protons, and the neutrons. That was one of the discoveries that was made by Rutherford. It was also observed the structure in which the orbit, is being designed. The orbits have different levels, and each of the levels had different number of electrons that they could hold. And this was one of those things that led us to wanting to understand more about the shell, the classification of the shells, the orbitals of the atom. Before we move any further, a short break will be taken as of this moment, and in a few seconds some questions will be displayed on your screen. Please answer them. We want to see how much you've understood what has been taught in this lesson so far. Welcome back. So, I haven't spoken about the Dalton's atomic theory and the structure of atoms. Let's look at some of the components of the atom. In the atom, there are certain things that we need to bear in mind. I talked earlier about the electrons and the protons, as well as the neutrons. So there are some specific numbers which we work with in the as regards the elements, and the first of them is what we call the atomic number. The atomic number. The atomic number is the number of protons present in one atom of an element. Is the number of protons present in one atom of an element, and it is what we use actually to position the element in the periodic table. Also, we also use it when we want to do certain reactions, that is calculations involving the particular element. Also, we have what we know as the mass number. The mass number. The mass number is the sum of the number of the protons and the neutrons in the element. Why do we take that as the mass number? When the components of atom, when the components of the atom were being examined, we have as I mentioned earlier, the electrons, the protons, and the neutrons. In terms of charges, electrons are negatively charged, protons are positively charged, and neutrons have no charge. In terms of mass, protons, if we rate a proton as 1 and we rate a neutron as 1, an electron will be about 0.0005. That is, the size, the weight, the mass of an electron is negligible. It's so small, it can be classified as nothing. So oftentimes we tend to treat electrons as though they do not matter when we are considering the mass number. So when we want to talk about the mass number of a particular atom, just take note of how many protons are in it and how many neutrons are in it. Also to note, the first 20 elements, we need to get familiar with them. The first 20 elements, you need to get very familiar with them. You'll be working with them a lot. We use this particular knowledge to arrange the elements in the periodic table. When the periodic table, in time to consider the periodic table, we'll be drawing it, we're taking a look at it, and we'll be talking about their arrangement. Okay, let's talk about isotopy. Isotopy is a phenomenon where a particular atom or particular element have two different types of material. That is, the element is one element, but it can exist in more than one type, more than one form. We'll talk about isotopy in substances such as hydrogen, such as oxygen, such as chlorine, and other elements as that. We have very many of them, very many elements which have different kinds of isotopes. How does isotopy work? How does it come about? In isotopy, a particular element, let me take for example chlorine. We know chlorine has mass number 17. The mass number is usually written at the bottom. Mass number is represented by a Z. That's what represents the mass number. It's represented by a Z, and it is written at the bottom part, left hand side bottom. And the mass, that's atomic number rather, is written bottom left hand side, while the mass number is represented with an A, and it is written top left hand side. So we have chlorine, which has a mass number of 17, atomic number of 17, and a mass number of 35. We also have chlorine, this same chlorine, same atomic number 17 and mass number 37. The question I know you want to ask me is, how is that possible? Well, it is very possible. We need to bear in mind, remember when we're defining mass numbers, atomic numbers, we define the atomic number as the number of protons present in the atom. The number of protons present in the atom. So, since number of protons present is 17, that means any atom that has 17 protons should be chlorine. But now we are having a condition where all of them have 17 atoms, 17 protons in their atom. But some of them now are having a mass that is bigger than 35. So the question we ask ourselves is, how is it possible? If we want to find out what are the components that make up the mass number, those are the protons and the neutrons. The protons and the neutrons. So it suggests that this particular one has how many neutrons? The number of neutrons in this can be calculated as the mass number minus the atomic number. So when we subtract that, we'll have 18. For this, the same thing, mass number minus atomic number, and we have 20. So this is a phenomenon that occurs, and we see it happening in almost every compound, almost every element. Most of the elements exhibit these traits. Talk about uranium, talk about oxygen, talk about even nitrogen, aluminium. We see them exhibiting some of these unique traits. This trait is called isotopy. It's a state where you have a particular element which has different types of substances, some of them having different, each of them having different mass numbers. Well, this contradicts what Dalton's theory states. Of course, there's one or two things. Let's consider something. Now, we use, in the terms of considering this isotopy, we use it in determining the mass number of elements which we do take cognizance of. There are certain things that also need to be known. One of those things is the abundance of the substance in nature. The abundance of the substance in nature. In nature, we have about 75% of chlorine 35 and about 25% of chlorine 37. So when we want to calculate the mass number of chlorine, what do? We multiply their abundance by the mass number, and we add and we find the average. The abundance by the mass number, we add and we take the average. So to do this, we say 35 multiplied by 75 over 100 plus 37 multiplied by 25 over 100. So when we enter this information into the calculator, we will have 26.25 plus this will give us 9.25, and when we add them together, we'll have a total of 35.5, and this is how we get the mass number for chlorine. So the mass number which we use to represent chlorine is 35.5. When we do that for calculation of oxygen, we have oxygen 16 and oxygen 18, and they have a proportion of about 86 to 14 percentages in nature. So if you do the calculation for oxygen, it takes you to about 16.2, which is approximately 16. So that's how we do the calculation for most of these compounds. We consider their abundance in nature. While compounds like hydrogen has so much of abundance of hydrogen 1. Let's consider the periodic table. What is the periodic table? The periodic table is a table that shows the different elements arranged based on their different elements arranged in a specific order, where we have vertical and horizontal lines to represent them in their periods and in groups. We have 8 major groups. We have more than that if we want to look at it in another perspective, but we have 8 major groups which we'll be focusing on at this point in time. And we also have about several different periods. When we talk about periods are horizontal lines, and they show how many shells we can possibly find in a particular atom, while the groups show the number of electrons that are in the outermost shell. It shows the valency of the particular atom. On your screen about now, you're seeing the first 20 elements arranged. You have the hydrogen, the helium. Our hydrogen atom finds itself across all the way. It is called group 1 or group 9 and group 7. It's either identified as both group 1 and group 7. It's the only one with that particular feature, because in that particular orbital where it is, there are only 2 electrons in the shell. So we have the hydrogen, we have the helium, which is the stable electron in that particular shell. We also have the lithium on the next, in the next period. We'll see lithium, boron, beryllium, boron. Then we'll see carbon. If you look at the colored one, we have carbon shaded in a different color to show it is a metalloid. We have the nitrogen, the oxygen, the fluorine, and then we see the neon again. Neon is also a stable gas. We have and the others follow afterwards up to calcium. Okay, so the periodic table, it shows rows and columns. On our vertical columns, we have the different groups being indicated, and in the horizontal, we have the periods. The periods are in the horizontal. Now, there is something we need to take note of. You see those guys in the group 0 or group 8, as whichever we choose to call them. Some classify them as group 0, some do classify them as group 8. Every one of them on that particular group are not reactants. They do not react in any chemical activity. They're just there as observers. They're just there as observers of chemical reactions. And why is that so? In the case of helium, I'll use helium as an example. In the case of helium, this is the nucleus and the outer shell. It has 2 electrons, and the shell can only hold 2 electrons. So it neither gives away its electron nor accepts any electron. Even when you are trying to force it on it, it will just keep looking because it is satisfied. It's like a boy that has eaten a full bowl of eba and is filled to the brim. It cannot accept anything from anyone. It cannot give away anything to anyone. The thing it has is just contented with it. And we know chemical reactions simply has to do with exchange of atoms, of electrons. So, let's talk about chemical combinations. We have 2 major types of chemical combinations. The first one is called the ionic or the electrovalent. The electrovalent bond. The ionic or electrovalent bond. This kind of reaction occurs when 2 substances, a metal and a non-metal, interact with each other. What happens? The metals give away electrons and become positively charged, and the non-metal accepts electron and becomes negatively charged. A good example of this can be calcium oxide. Calcium oxide. It contains 2 different atoms. We have the calcium, which naturally have 2 valence electrons in its outermost shell, and we have the oxygen, which has 6 electrons in the outermost shell. Let's say this is our calcium. This is a core. It has 2 electrons here. It has eight electrons. And there is another shell where there are just 2 electrons. Now, our calcium has eaten and is filled, and he has leftover food that he wants to give away since he can no longer eat. If he's supposed to eat, he will need a lot more food to be satisfied. So we have our oxygen, which has the core, oxygen is there, seeking to get something from somewhere. Now, this calcium simply releases these 2 electrons in its outermost shell and dashes them out to oxygen. So we have something like this occurring there. And for the oxygen, it has something like this. Okay, I think it's about time I use different notations. Let me use X's to represent oxygen. And O's to represent the calcium. So we can have a clearer picture of what is actually happening. So, the oxygen accepts some elements, some electrons from the calcium. Now that our calcium becomes +2, our oxygen becomes -2. This plus and this minus makes them get attracted one to the other, just like magnets. You have opposite poles attract each other, so it brings about an attraction between the 2 of them, and they tend to stick together. Electrovalent bonds are known to form solids mostly, and where solids are formed, they have very high melting points and very high boiling points. They are known to form crystalline substances. Electrovalent bonds are known to form crystalline substances. The other bonds are, we have the covalent bond. The covalent bond. In the covalent bond, covalent bonds are usually formed between 2 non-metals, or sometimes between a non-metal and another atom of its own. A very good example of such a bond, that's covalent bond, is the oxygen molecule. The oxygen molecule, which exists in O2. Of course, I won't be drawing the inner core now, I'll just be drawing the outermost shell. We see something like this. And then these 2 atoms come together and form something like this. They come together and form something like this. Now, covalent bonds involves sharing of electrons. Sharing of electrons. Both parties share. They have enough, each of them need 8 to naturally be stable. So now 1, 2, 3, 4, 5, 6, 7, 8. It's complete. We have shared. And of course, if this E2 wants to count his own, 1, 2, 3, 4, 5, 6, 7, 8. It involves sharing of electrons. Now, covalent bonds can be classified into 2 types. We have the ordinary covalent bond, and we have the covalent, coordinate covalent bond. The ordinary covalent bond and the coordinate covalent bond. This one is what we know as the ordinary covalent bond, where they do share the number of electrons such that everybody is comfortable. In the coordinate covalent bond, what do we have? We have situations of what we will structures as ammonium, structures as hydrozonium ion. In these structures, one of the electrons, one of the atoms joins to the other atom without it supplying anything to the system. It does not make any contribution to the system, but it is just accepted as part of them. In this particular case, in the case of this hydrozonium, we have water plus hydrogen ion. Hydrogen ion just attaches itself to the system. It does not make any contribution to the system. Generally, covalent bonds are weaker than ionic bonds because of the nature of their existence. It involves sharing of electrons. Nobody can claim ownership of any electron. While in ionic bond, the force of attraction between them is the positive and the negative charges. Thereby, it has a very firm source of attraction. Other than these two bonds, these are the two major bonds. We have other bonds such as the hydrogen bond. The hydrogen bond is a kind of covalent bond which usually exists with hydrogen, where hydrogen is actually involved. We know that hydrogen can be a plus element or a minus element. It can give away just as much as it can receive. Therefore, because of its instability in decision, it tends to form a very weak bond. Because of its instability in decision, it tends to form a very weak bond. It can decide to give and it can decide to receive. So oftentimes it shares. Alright, apart from the hydrogen bond, we also have the van der Waals forces. The van der Waals force is a kind of bond that exists between gliding substance atoms. These atoms do not, in fact, it's as though they do not have any relationship. It's like as though they are not connected one to the other. But these forces just keep them within themselves. And it is actually the weakest of all the bonds, of all the chemical bonds that do exist. Okay, let's now consider all the things that we have talked about today and let's look at it. How do they relate to the Dalton's atomic theory? Dalton's atomic theory. Of course, earlier we stated the Dalton's atomic theory. We stated the 5 of them. We said the first one states that an atom, L particle, is made up of an indivisible particle known as the atom. Rutherford proved Dalton to be wrong. Dalton made this suggestion in 1808. Rutherford in 1911, he came up with another experiment and he discovered the existence of the proton, the neutron, and the electron. So it is proved that the atom is not indivisible. It may be the smallest form in which an element exists, but it is not the smallest indivisible part of matter. The second law, or second part of his theory states that atom can neither be created nor destroyed. Well, this theory holds still because we have proved over and over that matter is neither created nor destroyed. It can only be transformed from one form to another. The third law states that all elements of the same compound are exactly the same, and they differ from those of other compounds completely. Well, this law has been scrapped because we discovered that argon, not neon, argon has a mass number of 40, atomic number of 18. Calcium. Calcium has a mass number of 20. Atomic number of 20, mass number of 40. We are seeing similarities between them. Apart from this, we also see what is called isotopy, where we see chlorine coming as 37 and also coming as 35. We see isotopy where oxygen is coming as 16 and is also coming as 18. So atoms of one element can actually have different nature. They may not be exactly the same at every point in time. And also atoms of other elements can look like the atoms of a particular element, especially when you are considering the mass number. The final of the Dalton's atomic theory states that when elements do react, they do so in small quantities. Well, when we consider structures, especially when we go to organic chemistry, we'll discover that there are structures that do combine at thousands of numbers, such as our polyethanes. Polyethanes can have 1 million structures or 1 million components of one ethane substance continuously connecting to each other. We can see them in many structures. Many different structures can have structures that are having 500 of carbons. Multiple structures as that. Structures like butane, peptane, all those structures, they have many different components and not small numbers, large numbers. So when we have such, it means that Dalton's law about them combining at little numbers does not hold. So Dalton's law has been modified because some of his laws do not hold after many years have passed, and we discovered that some of those theories have been proven to be false. Alright, in this lesson on atomic structure, we looked at the Dalton atomic theory. Talked about the 5 of them. We also talked about the atomic structure, how the atom is being structured, the components of the atom, that is the proton, the neutron, and the electron. We talked about their charges. We talked about atomic number, that is the number of protons in an electron, and so in an element or in an atom of an element. We talked about the mass number, which is the sum of the protons in the element and the sum and the neutrons in the same atom. We talked about isotopy, where it's a phenomenon where we have an atom having different mass numbers but the same atomic number. We then explained the periodic table, defining the rows and the columns. The rows, that's the horizontals, to identify the period or number of shells which the element has, and the columns indicating the number of electrons in the outermost shell. Each of these has effect on the properties of the atom. Also, we talked about chemical combinations, where we mentioned the 2 major forms of chemical combinations, which are the covalent and the electrovalent bonds. And then we looked at the modification of the Dalton's atomic theory, some of the theories which were cancelled and some which were modified to suit into further discoveries that were made over time. I haven't talked about the atomic structure. Some questions will be displayed on your screen in a few seconds. Please attempt them. And if there's any part of this lesson which you think you missed out on, you can go over the video one more time for better clarity. Thank you.